You can start recording. I can start.
Okay. If everything is if everybody's happy with that, let's go ahead.
Yeah, I start.
Okay. Thank you and welcome everyone. And happy to present Samuele at Centorrino from Stony Brook University. And Samuele is doing some very interesting work, in particular on stochastic frontiers. Samuele, we have about an hour, and are you fine with being interrupted with questions, or do you want questions?
Most definitely,
yeah?
Yes.
All right, so let's just get rolling, and so about an hour plus or minus, but take it away. Thanks.
Thanks, Artem. Thanks everybody for the invitation. So again, please feel free to stop me, interrupt me at any point. If you have questions, just shout at me, because sometimes when you raise your hand in the Zoom room, I don't really notice. So today I'm going to be presenting this work with a joint work with Maria Perez-Rudiales, who is at the Inter-American Development Bank, Boris Bravo-Reta at the University of Connecticut, and Alan Wall, who's at in Oviedo in Spain. So what we're going to try to do in this paper is basically to take a stochastic frontier model, a pretty standard, let's say. I'm going to try to introduce a bit the model that we use for those who are not familiar with this literature. And then we're going to try to introduce in this framework a binary endogenous treatment. And I will explain I will try to explain why what we do here is different from what has been done in the past, and also I will try to explain some of the technical contributions of the paper, and also some of the technical challenges that we face when we want to estimate this type of models. So let me go ahead and get started. So the so the motivation, the empirical motivation for this paper is that there has been an increasing pressure on agricultural sector, especially with climate change. So with increasing floods and drought, there is a need to improve global efficiency in the agricultural sector, and that's basically something that has been stated very clearly in the Sustainable Development Goal number 2 of the United Nations. So there are many international organizations, including the World Bank or the Inter-American Development Bank, which are trying, therefore, to implement some programs at the smallholder farmer level especially in developing countries. And actually, stochastic frontier analysis, it's a very useful tool to evaluate the effectiveness of these programs. So, of course, the point is that these programs are often not randomized, so they're not randomized controlled trials. So the participation into these programs often occurs on a voluntary basis, and therefore it generates a selection bias. So there is basically a selection into treatment here, because participation is not random, let's say. So the point is that how do we control for this selection bias when we actually estimate that we want to understand the effectiveness of these programs using stochastic frontier models. So what do we do in this paper is basically we try to propose a method which is in principle very straightforward, which is basically maximum likelihood. So we're going to be making assumptions about, we want to make distributional assumptions about the error term. And we are going to allow for selection biases. So we're going to allow for the treatment assignment to be correlated with unobservables. And in the particular case of the stochastic frontier model, since the unobservable is the convolution of two components, that makes the construction of the model more challenging than in the standard regular case where you have a regression model with endogeneity and you're trying to control for it. So again, this is a maximum likelihood framework. So we're going to set up a framework in which we jointly model. So we're going to have an IV type of framework. So we're going to have an assignment mechanism which is going to be auxiliary and is going to tell us, given observables, what is the probability of each farmer to undertake the treatment. And then we're going to be basically construct this maximum likelihood in closed form, which is basically something that it's not particularly easy to do, and we are actually getting some traction in that respect, like in trying to provide this likelihood function in closed form. So it's not like I am against, so one could do simulated maximum likelihood, and this is something that I will mention at some point. There is nothing wrong with that. The point of doing of writing down the likelihood in closed form is that it allows us to have a conversation about certain things like identification, which usually is very difficult to settle down when we are doing simulated maximum likelihood. And then we conclude with this empirical application to this. We have data on a policy intervention in El Salvador to promote soil conservation practices. And I'm going to show you a little bit the results in that empirical application. Comparing what happens when we don't control for potential selection bias, so we don't control for endogeneity, and what happens when we actually implement our framework and we control for endogeneity. All right, so let me just get started with the model. So basically, I'm going to start. I mean, some of you are going to know this, so I'm just going to, especially Artem is going to know this, but I'm just going to do it because it's just a review to understand exactly what we're estimating. So let's say that you have a sample of N farmers that they're using some inputs, which I'm going to call Xi, to produce an output that I'm going to call T star. And then there is a production technology, which is homogeneous. It's the same for everybody. And we're going to take the production technology to be known up to parameters. So there's a parameter beta, which is unknown to us. So the idea of the stochastic frontier is that basically this production technology is the maximum output that can be produced for a given bundle of inputs. But farmers might actually fail to produce at that level, so there is going to be a gap between the production frontier and the actual observed level of production, and that we call that thing inefficiency. So there's going to be this difference between the observed level of production and the optimal level of production. So
what is beta?
Beta is a parameter, is a production function parameter. It's so let's say in the simplest case, you can think M is a Cobb-Douglas. You have two inputs, so beta will be the parameter of the Cobb-Douglas production function.
Thank you.
Okay, so basically we have this gap, and then since this is a stochastic model, we add to this stochastic error term, which is because sometimes we observe, for instance, the output is observed with error. So we add to this a stochastic error component. So just to clarify the idea, this is a figure. So you see that there is, so here I'm setting the measurement error to 0. So there is no stochastic component in the model. And there is just, you see that the production frontier. So there are some farmers which produce exactly at the frontier, but most of the farmers produce below the frontier, and the distance between the actual level of production T and the optimal level of production T start is going to be measured by this inefficiency component. So if I take the model in log, I get this regression type model in which I have yi, little m of xi and beta, plus the stochastic error component and the inefficiency term. So notice that the inefficiency term, so here I'm considering a production framework, so the inefficiency term is strictly positive. So the negative of it would be, it would be negative or 0. Okay, so that is because it measures the gap between the actual level and the optimal level. So in this framework, again, you see that the difference between this framework and a standard regression type framework is that I have two error components. These quantities are both unobserved to the econometrician. And basically what I'm going to try to do is to add into this framework a treatment dummy. Okay, so there is a participation dummy Z of I. And I'm going to suppose that this participation dummy can affect the model in two ways. So can either shift the frontier, so it can change basically your production technology. Okay, so it's not necessarily an input, but This is what usually people in this literature call a facilitating input. So it's going to help you use your bundle of inputs in a different way. So again, in the case of a Cobb-Douglas production function, this might change the way, let's say, the marginal returns for each inputs. And then you're going to have the stochastic component, which I'm not going to touch in this particular example. And then you're going to have a function g, which is going to scale inefficiency up or down. So you're basically going to have a baseline level of inefficiency. So when you don't participate to the treatment, that function g is going to be equal to 1, and then the treatment is going to scale up or down your inefficiency level, which implies that it might reduce your inefficiency, so it might actually help you get closer to the frontier, or it might actually have no effect, or actually increase your distance from the frontier. So that's the way we model in this paper the effect of the treatment. So the treatment can either be having an effect on your production frontier, or it can have an effect on your inefficiency level through this scale function g. So basically what we want to do here is to estimate the parameter delta and beta, and again, it's like in this case, I'm just keeping it simple. We just have production inputs x, we just have the treatment z. Of course, we can add a bunch of other variables that are exogenous that can also affect either the production frontier or the inefficiency function g, and that's usually done at the, let's say, it's an economic reasoning why we add more variables. We just decide which variables enter in which part of the model. That's what applied people usually do in practice. So, but for this presentation, just keep it simple. We have inputs x and we have the treatment z. Okay, so we want to estimate the parameters beta and delta. Of course, in the standard framework, and we are also interested in estimating the technical efficiency. So technical efficiency is basically the exponential of the negative of ui. So it gives me really the distance between the actual output produced and the optimal output that the farmer should produce. So in this literature, it's commonly accepted that in order to estimate technical efficiency, we need to make assumptions about the joint distribution of V and U, okay? So in a usual framework, in the most standard textbook framework that you have, if you want to estimate beta and delta through maximum likelihood, what you're gonna do, you are gonna assume that V is independent of U, so these two components are independent of each other, that V follows a normal distribution and U follows a truncated, or a half normal distribution, so it's a where there is strictly positive. So it's an half normal distribution on the positive real line. So with these assumptions, it's very well established that you can get an estimator of beta and delta, and you can get an estimator of technical efficiency. Now, the problem is that we have here is that, of course, the treatment is endogenous, so the assumption of independence does not bite here. So again, I'm still going to assume that the inputs are independent of V and U. We can enlarge this framework to allow for endogeneity of the inputs. Artem has worked on this issue. I have myself worked on this issue, so that's not something that we cannot do, but again, for the sake of simplicity, let's assume that the X are still independent of the pair VU, but we cannot assume that the treatment is independent of V and U. That's exactly what the contribution of the paper is about. So the treatment is not going to be independent of the components V and U. So you can think about this lack of independence as the fact that V often can include individual preference or omitted variable that are unobserved to the econometrician, and that can be correlated with the propensity to take the treatment, let's say. And then UI represents other unobservable, like soil quality, for example. Soil quality is only known by the farmer, but not known by the econometrician, and therefore it might actually affect the probability of the farmer to overtake the treatment or not. Okay, so this is the idea behind the paper. So again, what we do here is fairly standard in some sense. So we're going to take, I mean, there is going to be an assignment mechanism a la Heckman and Robb. This assignment mechanism says that given observables and some parameter gamma and a stochastic component eta I, the participant will take the treatment if this quantity is greater or equal to 0 and will not take the treatment if otherwise. So here the W tilde are instruments, so WI, which I'll denote instrument as instruments, and then it will also include the inputs, because again, I'm taking inputs as being exogenous, so I'm going to enlarge the set of instruments here to include the inputs xi. So again, imagine this was in a standard assignment framework here, where this is a latent equation, latent model, so eta I cannot be estimated. So in some sense, you can think about this as a standard, let's say, probit model. So in standard probit model, what you do is that the first thing that you do is to assume that W tilde is independent of eta, and that already gives you some bite in the identification process. So if that's true, if W tilde I is independent of eta, then all the correlation or all the dependence between the treatment assignment or the propensity to take the treatment and the inputs, and the error components is actually captured by this term eta. And so we will refer to eta as a control function. So basically, it's a variable that if you control for it, then the dependence between the treatment and the error term will disappear. And in particular, this implies that in statistical terms, if eta is the only route through which the treatment z is dependent on v and u, then we also have that z is independent of v and u once we control for eta. Okay, so that's basically what I have said before in different words. So we are going to complete it with the following assumptions that are basically a generalization of what is done in the literature. So remember what I've told you before. Before I've told you that in a standard framework, I would assume that v and u are independent. Here, I'm going to assume that v and u are independent given eta. So once I control for eta, every dependence between the two stochastic components in the model would disappear. And then these three assumptions are the ones that allow me to write down a maximum likelihood estimator. So I'm going to assume that eta follows a standard normal. So basically, with this assumption, this model becomes a probit model. Okay, so that's a probit assignment mechanism. I'm going to assume that conditional on eta, vi follows a normal distribution, and I'm going to assume that conditional on eta, u of I follows a folded normal distribution. And I will just get into some of the properties of this distribution in a minute. But what you can see here, that I think it's very nice, and it's in the standard. I mean, if you think about it, this is again in the standard models which control for endogeneity. You have two parameters, rho u and rho v. These two parameters, rho u and rho v, control the dependence between the treatment and the unobservable components. So if these two parameters are equal to 0, then you are back to the standard stochastic frontier model in which these two terms are independent of the treatment. So you can, from the point of view of the practitioner, you can test whether that dependence is actually playing any role or not. And so we see this effectively as a generalization of that particular model. So we estimate this model, we can test whether the other model holds true or not. So let me go a little bit into this folded normal distribution. I mean, basically the idea here is that, so this is the PDF, the conditional PDF of u given eta. So here you see that, again, for those of you who are familiar with the standard stochastic frontier framework, when rho u is 0, the density collapses to the truncated normal, the half normal, positive half normal distribution. So you see here, this black line is when eta is equal to 0, which is the same as saying that rho u is 0 in this case. I mean, numerically speaking, at least, this is a half normal distribution. So when I change eta, this basically shifts the mode of the distribution, and the mode of the distribution, I mean, in this case, I'm shifting eta to be positive, but the mode of the distribution shifts to the right. So something that I would like you to notice, and this is something that is going to be important for some of the technical issues that we're going to discuss later, is that this distribution is kind of symmetric in rho u. So if I, let's say, take rho u equal to, since I have here a negative sign and here a positive sign, so if I take rho u to be negative, or if I take rho u to be positive but of the same value, the density that I generate is the same. So basically, think about this as at 0, you have a half normal distribution, and whether you move rho u either to the left or to the right, you get the exact same. Observationally, the distributions are equivalent. So that's going to be important for identification, and this is something that I'm going to discuss later, because effectively we cannot identify the sign of rho u. So we were going to restrict rho u to be in the positive interval 0, 1. So again, rho u, you can interpret it as a correlation parameter in the standard sense. So it takes values between -1 and 1. But because of this identification issue, we are restricting its support to be 0, 1, because we will not be able to identify the sign anyway. So, okay. So what do we do here that it's different from what has been done before? So basically, the idea of going through the troubles of writing down this model in closed form and deriving the maximum likelihood in closed, the likelihood function in closed form, is because we want to estimate technical efficiency. So estimating technical efficiency, one of the most important features of stochastic frontier models. People use technical efficiency to rank farmers and to reach policy conclusions. So there are papers who have tackled the issue of estimating these models when there is endogeneity of the treatment, and in particular, there is a recent paper by Chen and co-authors in the Journal of Business Economic Statistics, who uses basically a weighted propensity score estimation in order to estimate the parameters of the model. However, the point about this paper is that since they are not making any assumptions about, so they are making assumptions about the marginal distributions of the error components in the end, but they're not making assumptions about conditional distributions. They don't have a likelihood function, so they cannot write down, they cannot provide an estimator of technical efficiency, which is something that it's nice for practitioners in this case, and for applications of these models in general. So one of the main issues here, that's something that, I mean, again, it's a technical challenge. I'm not going to go into the computations, but again, in the paper that I have with Maria Perez that just came out in the Journal of Econometrics, we use a similar framework, but we assume, I mean, it's a similar framework, but in our framework, the treatment is continuous. So in that case, you can think about eta as being observed, at least for identification purposes. So in that framework, you are basically writing the likelihood using the conditional densities. Here you cannot do that because eta is latent. You don't have the possibility of using the conditional densities. So you have to derive the conditional CDF of the latent variable given the composite error term, so given this epsilon, which is v minus u. So that is actually part of the contribution of the paper, is actually to do that, which is, again, not particularly interesting from the point of view of the computations themselves, but it's important because it's really the step that allows us to do everything analytical. So basically what we do, we take, I mean, we have the conditional density of eta, of epsilon given eta. Again, epsilon is the composite error term, and we need to multiply this by the marginal density of eta, which in this case is a standard normal distribution. So I'm going to use the notation phi for standard normal distribution, and we will have to integrate this with respect to eta in a certain interval. So again, one could do this with simulated likelihood. So I know the distribution of eta, it's a standard normal. I know the conditional density of epsilon given eta because I know it from my previous paper. I can just simulate eta from a standard normal and then integrate it out numerically. So again, this might be computationally costly. There are other issues related to consistency of the simulated maximum likelihood estimator. So we go with a direct approach. So again, I'm not going to give you the exact expression. It's not very beautiful to see. But basically, the idea here is that I'm going to decompose these terms into two parts. That is going to be the conditional CDF of eta given epsilon. That's going to be kind of a first stage likelihood. And then there is going to be the component of the likelihood that is coming from the stochastic frontier model. So when your dependence parameter are 0, it's like you're estimating these two models completely separately. This first stage becomes the likelihood of a probit model. This is the likelihood of a standard stochastic frontier model. So what we show is that basically we go by deriving the joint density of eta and epsilon and then integrating eta in a certain interval analytically. So what we show in the paper is that the joint density is a mixture of two skew normal distribution, which again, we know that that's going to create us problems, but in identification. So because the mixture probability depends on this parameter rho u, which captures the dependence between the inefficiency term and the treatment. When rho u is equal to 0, the mixture disappears, so the mixture are the same. With probability 1.5 and probability 1.5, I'm drawing from the same distribution. So I'm going back again to a standard framework in which that has been analyzed in the stochastic frontier literature, where I only allow for one of the components, which is the stochastic component, to be correlated with the treatment. So using this result about the joint density, we can actually derive the conditional CDF of eta given epsilon and then the marginal PDF of epsilon. And then we use that to basically construct the likelihood function in closed form. So this is, again, yes, go ahead, Dr.
So suppose that you assume normality throughout for the underlying U, V, and eta, multivariate
Yes.
normality.
Yes.
You could, in principle, derive this limited information likelihood based on that. And the question is then, how is that different from what you're doing?
Is not different, conceptually is not different. I'm still doing the same thing. I'm still deriving the likelihood function, and I'm still writing down the joint density in this case, which is a joint normal density in your example, and I'm basically integrating eta out in a certain interval. So conceptually, it's exactly the same thing. The technical contribution here is that we don't know what is the likelihood in closed form for this class of models, exactly because of the challenges posed by the fact that the marginal truncated normal, if you wish, for U, which is conditionally on eta, in my case is a folded normal, makes everything more complicated analytically to derive. But conceptually, you're totally right. It's not new. This is what people do all the time when they want to control for endogeneity in a standard maximum likelihood framework. So I'm just following textbook type of thing. It's just that all the results that we derive from this standard approach are new to my knowledge, that there is no result available of this sort that I'm aware of, at least. Okay, so again, so let's go back to, okay, so the likelihood function, again, this is standard. Again, likelihood function, I have z and I have y. In order to write the likelihood function, I have to weight. So I have a Bernoulli, basically, again, so that's standard with probability 1 minus f. I participate to the treatment. With probability f, I don't participate to the treatment, and then I have the likelihood function from the stochastic frontier. And basically my parameter, which is So my parameter here is, so remember beta and delta, which is the first step parameters, gamma, which is the parameter of the assignment mechanism. And then I have all these dependence parameter, rho v, rho u, the variance of the inefficiency component, sigma u and sigma v. So basically the log likelihood function is the log of this. I'm maximizing this with respect to the parameter theta, and this is, again, very standard. I'm going to get the likelihood function. So even if I assume, so I want to go back 1 second, because the main innovation of the paper, as Artem pointed out, is to allow for this particular distribution for the inefficiency component. So something that we discuss in the paper and that we also discuss in some length in our Journal of Econometrics paper is that if you, and I think this is quite of an interesting feature of these models, is that, so let me suppose for a second that all the parameters here are first order identified. So what I mean by first order identified is that when you write down the system of equation defined by the score, that system of equation has full rank for all the parameters except rho u. So you have a system of equation with full rank, and you add one equation, which is the one that allows you to identify rho u. So because of the problem that I discussed before of the symmetry of the conditional PDF of u given eta, this is what happens to the likelihood. So here I take all the other parameters to be fixed. I set rho u to 0.5, and I set sigma u to pi divided by pi minus 2. So this, you see, is the likelihood function, that the profile likelihood for rho u. You see that here, the true value is 0.5. The likelihood has two maxima at 0.5 and negative 0.5. And then he also has a local minimum at 0, because of course, since he has two maxima, he has to flip back in order to create this problem. So what I'm going to do about this, as I was mentioning before, I'm going to fold it. So I'm going to fold the distribution. I'm going to remove the negative axis from my parameter space, and I'm just going to allow rho u to be positive in the 0, 1 space. There is still another issue here, which is that at 0, you always have a local minimum. So the score for rho u at 0, even if the true value is 0.5, here the score is going to be equal to 0. And actually, something that we show is that it's not that it's just 0, it's going to be 0 for any value of the other parameters. So for whatever value you set all the other parameters, the score for rho u equal to 0 is going to be always 0. So that is what people call a lack of first order identification. So when you have the score that is identically 0 at some point, it means that the score cannot identify that parameter, because it's always going to be 0. Whatever the true value of rho u is, it's always going to be equal to 0. So basically, you have to go to higher order derivatives, and that's why it's called higher order identification. So if you go to the second derivative, that second derivative is going to be 0 in expectation, which is what you would expect from a score. So what you're basically identifying, you are rewriting the likelihood in some sense. Instead of writing the likelihood as a function of rho u, you're writing the likelihood as a function of rho u squared. So this has implications for many things, because remember, if you want to do, let's say, inference, you cannot do inference based on the score test, because the score test is going to be equal to 0 at 0 all the time for any value of the other parameters. So it's going to have no power to detect deviation from the null that rho u is equal to 0. So all these issues arise in this model, and that's just one of the issues. And I'm not going to enter in other identification issues that arise when, for instance, the variance of the inefficiency term is equal to 0, because I'm assuming that away, but I'm going to focus on this particular issue. So, and the second problem is for the rate of convergence. I mean, when rho u is equal to 0, the rate of convergence, because I go to higher order of identifications, is not going to be the square root n standard type rate of convergence, but it's going to be n so it's going to be the n to 1 over 4. So it's going to be slowed down by the order of identification. So otherwise, if that's not doesn't happen, so if the row u is inside the 0, 1 interval, then I have no problem. My maximum likelihood estimator is standard, so I can do inference in the usual way. I have my distribution with the information matrix. Wall type confidence intervals would work. Standard trinity of tests would work, so I have no problems. I just have this problem at this particular point of the parameter space. So this is the formal proposition. So here we show that basically so if we assume that rho u is the true, 0 is the true value of rho, for all the other parameters fixed at the true value, we have a symmetry in the likelihood, in the score. So the score at evaluated at rho u in expectation is 0. It's also going to be 0 when evaluated at negative rho u. So that's the symmetry that I was showing you before. And this is the fact that the score is identically equal to 0 for rho u equal to 0. And again, this is not a typo. This is for every value of θ1. So here I don't need to set θ1 to its true value. Is that for any value of the other parameters, when rho u is equal to 0, the first derivative is going to be equal to 0 when rho u is 0. And therefore, I have to go to the second derivative, and the second derivative is going to be in expectation equal to 0. Okay. So estimation, again, standard, plain vanilla textbook. I write down the likelihood, the log likelihood. I maximize this given the restrictions on the parameters that I explained before. And this gives me an estimator, which I assume is consistent. One can potentially prove consistency. All the conditions are satisfied here, but just not to have to prove it. I just assume that it's consistent estimator of the true parameter theta hat under the identification restrictions that I have imposed. So again, if rho u is in the interior of the parameter space, I'm assuming that all the other parameters are locally identified, standard, maximum likelihood. I have a standard normal distribution. The variance is the inverse of the information matrix, and I am good to go. So I can do inference the standard way. I can construct the confidence interval the standard ways. Everything as the usual interpretation. Now, when I am at 0, when rho u is equal to 0, things change a little bit. So in this theorem, what we do, and again, this is following from theory that it's available. There is a seminal paper. There are several papers by Andrews at the end of the 90s and the early 2000s where he looks at testing for a parameter that is at the boundary. This is slightly more complicated because we also have that at the boundary point, we don't have first order identification, we have second order identification. So it's slightly more complicated, but the idea of the result is the same. So basically, if I denote rho u as the square of rho, what I have here is that the distribution of the other parameters is still going to be a normal distribution, but the distribution, the asymptotic distribution of rho u is going to be a half normal. So I'm going to have, I'm going to be at 0. Actually, sorry, I said something that it's incorrect. It's not going to be a half normal. It's going to be a distribution that is going to have a mass point at 0 with probability 1.5. This variable is going to be 0, and with probability 1.5 is going to come from a normal distribution on the positive real line. So basically, this distribution is non-standard, and you see that that this is going to create us problems when we want to, again, do inference, confidence intervals testing at the rho u equal to 0 is not going to be standard. We'll have to find other ways to do inference in that case. Okay, so so that's exactly what I say. So if you want to test, there are tools out there. So we are not inventing anything here. We're just trying to use results that are already available in some sense. So if you use all the results by Andrew, he proposed a set of tests so he proposes like modifications of the trinity of tests when the parameter is at the boundary. the point is that in this case, the parameter is still first order identified. It means that at the boundary, the score is not identically equal to 0. So what we do here, we can still use the likelihood ratio test, because the likelihood ratio test, we know its distribution if we want to test rho u equal to 0. So I want to emphasize, and I'm sorry if I have to go step back, that this is important, because as an applied person, the first thing that you want to test is whether there is endogeneity or not. So testing for rho u equal to 0 is one of the standard things that you want to do once you have estimated this model. So let me trace back. So the likelihood ratio test, since I have this distribution which has a minus point at 0 with probability 1.5, and then it's a half normal. Basically, what I can do, if I square that, I get a distribution that it's an equal mixture of a mass point at 0 and a chi-square 1. Okay, so I can still write down the likelihood ratio statistic in the same form, except, so the likelihood ratio statistic never changes. Its asymptotic distribution is different in this case, but I know what that distribution is, so I can still do a likelihood ratio test. So there are these two papers it's actually an old paper by Botai in Biometrica, and then a more recent paper by Ekval and Botai, which is to appear in the Annals of Statistics, where they propose a modification to the score to account for higher order of identification. So basically, when you do your score test, you would take the first derivative, because you know that deviations from the first derivative being 0 in expectations are signs that you are violating the null, right? So here what they do, they simply take higher order derivatives. So instead of taking the first order derivative, they take the second order or the nth order derivative, depending on which level of identification you have. So that modification of the score test, which is actually very interesting, they show that has the standard chi-square R distribution, where R is the number of restrictions under the null. So this is a pretty interesting result, because basically it would allow us to use the same asymptotic theory we usually use for testing, and that is going to actually is going to actually allow you to do things in a standard way. So getting confidence intervals is slightly more difficult, because in that case, again, remember that's not exactly the same. So it's like we can invert the test in some sense. We can always do that. So in some principles, you cannot use wall-type standard confidence intervals, because again, you have this non-standard asymptotic distribution, but you can invert the two test statistics. So you can invert either the likelihood ratio test, or you can invert this score test by Ekval and Botai, which you know is going to have the standard chi-square R distribution. You can do other things. You can do subsampling, and you can do M out of N bootstrap. We know that these two procedures are consistent. There are results, but they might not cover uniformly the true parameter in every portion of the space. So there is some, let's say, pushback on using these methods for when you have parameters, especially when you have parameters at the boundary of the parameter space. But in some sense, it's like we have these identification issues, but I think that we can reasonably say that we have tools out there that can allow us to provide, reasonable inference procedures for practitioner to use this method in practice. Okay, so finally, the technical efficiency, which is the latest contribution of, well, what I believe is another contribution of our paper. So in the paper by Artem and co-authors, they estimate the technical efficiency using the distribution of U conditional on epsilon and eta. Again, the problem here is that theta is not observed because it's latent, so we have to use the standard approach and estimate the technical efficiency from the distribution of U given, from the density of U given epsilon. And then again, this is just pure computational. We just take the conditional density of U given epsilon and eta, the conditional density of eta given epsilon that we have computed, and we integrate eta out. That gives us the conditional density of U given epsilon, and then we can derive the technical efficiency estimator, again in closed form. And details of all of that are given in the paper. So let me see how much. So I think I have about 10 minutes. So I'm gonna skip the simulations. I mean, in simulations, everything works as expected. So there is no particularly anything to say. So I'm gonna go directly to the empirical application. So we have this sample of farmers in El Salvador. This program that was run, it was back in 2005. Actually, the first round was run in 2002, and then there's the second round in 2005, where we have sampled participants in the program and a control group of non-participants. So the target population of these programs were, again, farmers, small farmers with income below the poverty line and producing mostly crops, staple crops such as corn and beans. So we're talking here about very poor farmers. And again, participation on this program was on a voluntary basis. So participants were deciding whether to participate or not in the program. So there are 15 different soil conservation technology that are proposed among participants. Again, here we simplify everything. We just say you participated or not in the program, and that's give us, and we're going to measure the effect of that participation on the production frontier and the inefficiency. So you can imagine that there was a lot of heterogeneity in the treatment, depending on the type of conservation technology that the farmers have used and for how long they have used it. So we're going to try to account for that by allowing the treatment variable to interact with all the observables that we have. So we are excluding any unobserved heterogeneity in the treatment that we cannot control for in this framework. We don't really have a way to do that, but we can still control for some observed heterogeneity between the control and the treatment group. So that's exactly what we do here. So think about the model that I wrote before. The production technology, the log of the production technology is linear. So we assume a Cobb-Douglas here. We don't want to get crazy. So the Cobb-Douglas is you have you have then the treatment Z2 entering in the production frontier. So you have the level of the treatment of 0, 1. It can shift your frontier, but it can also change the way you use your inputs. So it interacts with the inputs here. And then you have the difference between you have the stochastic component, you have the inefficiency component, and the scale, and the scale function G is taken to be the exponential function, and the exponential function contains other variables, which are the Z1, the treatment variable, and then again, it includes the interaction between the treatment variable and all the other variables. So we have 459 farmers, including control and treatment group. If I am not wrong, the percentage of treated is about 40% of the total of this. Again, inputs are land, labor, fertilizer, pesticides, and seeds. We control for a lot of environmental variables, a lot of Z. So we control for land because we think in environmental variables, because we think that the amount of land that you have is also going to affect the inefficiency, especially if your land is subject to erosion. There is the tenure, so how much of your land you own. We interact these two variables. We include use a standard age, education, a dummy for external sources of income, whether you have only food access to your plot, or whether you also have car access, and we have an index for risk diversification. And again, Z2 is the participation dummy. So as instruments, El Salvador is a country that it's affected by a lot of natural disasters, by earthquakes, tsunamis. There are a lot of volcanoes. So there was an earthquake in 2001, 1 year before the program started, that was very destructive. And we used the distance from the epicenter of the earthquake as an instrument to determine participation in the program. And then we also use other instruments. There are electricity. So how many families in the municipality where the household lives have electricity in their homes, what's the proportion of those who have bathrooms, and we use the external wage that is available for other jobs that they can do outside of the cultivating their land. So we do a bunch of diagnostics. So all of that is in the paper. So first of all, one might be worried that the assignment equation is misspecified. I use a probit model for the assignment equation. So you might be worried that that's misspecified. We test that using a test proposed by Wilde. We don't find any evidence that the probit model is misspecified. So we're able not to reject the null of a correct specification of the model. We also try to test, I mean, if some of you is aware of how to test instrument in this setting, I would be taker. I haven't found any formal result about this so far. In the binary setting, we just compute a likely ratio test. We compare the restricted model with no instrument with the unrestricted model with no instrument. So we compare, the unrestricted model with the instrument and the restricted model with no instruments. And we find a very large value of the ratio statistic. If we say we want to use the Stochastic rule of the F test, we think that instruments are still sufficiently strong. And then we estimate the model and we test for the inefficiency to be uncorrelated or not dependent to the treatment assignment, and we cannot reject the null that rho u is equal to 0. So we actually using either test statistics. So we basically, I proceed and show you the results when rho u is restricted to be 0, because the results when rho u is unrestricted are basically equivalent. So I'm gonna estimate the model restricting rho u to be equal to 0. Okay, so I mean, the model is quite complex, so I'm not going to show you all the results here. I'm only going to show you the effect for the levels, not for the interaction terms. Most of the interaction terms are actually not significant, so there will be no point in showing you that. So these are the production inputs, and again, everything is fairly similar across the two models. There is no particular difference, which is also, so, okay, sorry, I forgot to mention this. Okay, the first three columns is the model with exogeneity. I have my estimate and I have my 95% confidence intervals. This model is estimated by assuming away any endogeneity. So I am assuming that V and U are independent. V is as a normal distribution and U as a positive half normal distribution. So here, and here I use my model with endogeneity, restricting U to be independent of the treatment assignment, because I've tested for this and I know that there is no support for rho U not being 0 in the data. So here I compared the two models, and in this case, results are very similar. There is no evidence that the participation to the treatment shifts the production frontier in either of the two models. So everything, I mean, again, I get slightly larger confidence intervals in the model assuming endogeneity, which is also something that often happens because of the instruments. Now, in the efficiency determinant, which is the part that is of interest to me, again, I get more or less qualitatively, I get very similar results. The coefficient that I'm interested in is the delta Z2. I want to see whether the treatment affects the level of inefficiency or not. And actually it does negatively, so it's good because that's what we would like the treatment to do, so to decrease the level of inefficiency, so to get the farmer closer to the frontier. In the exogenous model, the sign is negative, but the confidence interval is very wide. Okay, so I cannot assume that this effect is, I cannot reject the null that this effect is not different from 0. However, in the endogenous model, where I control for endogeneity, I get a pretty larger and significant treatment effect here on the inefficiency component. So here I get what I expect. In some sense, I expect the inefficiency to decrease when you participate in the treatment, because that the soil conservation technologies would allow you to improve the quality of your soil and should decrease indeed your inefficiency. So finally, I want to present so we set rho u to be 0. So there is no particular interest there. So there is no dependence between U and eta, but there is a fairly strong dependence between B and eta. So there is a preference component, idiosyncratic preference component of the farmers, or it includes omitted variables, which is correlated with the let's say probability of overtaking the treatment. So and it's actually positive. So it seems that there is a positive selection. There are some farmers that are willing to enroll in this, and they actually do enroll in the treatment. And then again, for the variances of the error component, I get qualitatively similar results, which is encouraging. The last thing that I want to present before I finish. So this is the summary of the results that we have discussed. This is technical inefficiency in the exogenous model. That's the gray line. I hope you can see it. And in the endogenous model, that's the black line. I plot the technical inefficiency for non-participants on the left panel and technical efficiency for participants in the right panel. You see that, I mean, yes, it looks like the exogenous model gives a little bit slightly higher inefficiency to non-participants, but then the role of the two densities flips in the endogenous model. So you see that the endogenous model says that participants are slightly more efficient than non-participants compared to the exogenous model. And I think I can probably stop here if there is any questions. So this is basically a paper in which we are trying to provide a closed form maximum likelihood for allowing a binary treatment in stochastic frontier model. We believe that this has important empirical implications because this can be used to evaluate the effectiveness of several programs that are run in developing countries and even beyond let's say the specific empirical application at hand. We believe that the practitioner would find the work in the stochastic frontier literature would find our framework appealing, and then we present some empirical evidence using a sample of farmers in El Salvador. Thank you very much for listening. Please let me know if you have any questions.
Thanks a lot. Thanks a lot, Samuele. I assume you can hear me.
Yes, I can.
Yeah, okay. I changed to headphones. Yeah, thanks very much. And let me send you my virtual applause.
Thank you.
And then ask maybe a question, or maybe invite people to ask questions if any. While the audience is thinking, let me just ask one or two things. So this makes perfect sense to me, and good stuff. What I have a question about is that distributional assumption. So, and the identification issue. So the second order identification comes from effectively the assumption of folded normal on U given eta, right? And that, so I guess it's basically just driven by that assumption. So I wonder if, and I mean, you probably have this in the simulations, but I mean, how restrictive would that be? And is there a way to completely resolve this identification issue by a simple change in the assumption of the distribution that we take for you? That's question one. And question two is, so there's many instruments here. There's also many environmental variables in the example.
Yes.
Of course, you could think about very many instruments, right? And there's of course a question also of what is environmental variable, what's not, I mean, if this is possibly an instrument. There's a long list. So the question becomes, how is there a way to so if this is a weak instrument problem, how would you be handling it? And if there's very many instrument problem, how would you be handling it? Is there a natural way to include this form of penalization here that would allow you to pick instruments automatically.
Okay. Thanks, Artem, for the very interesting questions. So regarding question one, I don't know. That's a good question. So I don't know if by making changes to the distributional assumptions, we are going to be able to overcome or avoid this identification issue. I think so. The reason why I like this framework personally is because, again, it gives me, so from the perspective of the distributional assumptions, it gives a generalization to the half normal, normal half normal stochastic frontier model. So we collapse to that. We collapse to that when there is no dependence, and that's something that's a feature that I find particularly nice, because basically that's one of the most commonly used specifications by practitioners who work in this area. I think that could be a very good question. Is like, is there a class of distribution or another class of distributions that would allow me to get the same type of results, like having a more general model, for which the standard normal half normal model is a subcase, and that would allow me to overcome this identification issue. That's something that we haven't explored so far, and it's a good point. I mean, unfortunately, I don't really have an answer for you because it's not something that we have done, but it's a good point. Regarding the second questions, in terms of doing penalization for instruments, I think it might be feasible, in the sense that you have a standard likelihood function, so you can add the penalty to it. I mean, let's say you want to do lasso on the instruments, you can add the penalty for a lasso penalty to the likelihood function. I mean, and select the instruments if you have many instruments. That should be relatively straightforward to do. So something that I forgot to mention, but the likelihood, so I estimate the full likelihood, right? So basically that there's no problem in adding. I mean, you could do it potentially in two steps, like you can select the instrument and then estimate the other component of the likelihood, but that would generate some post-selection issue, right? Most likely. But you could do it in one step. So you could write the full likelihood. You have a penalty parameter for the gammas, which are the parameters of the instruments, and then you can do a select. You can basically select the instruments in this way. I think that's probably something that is also very interesting, that is related to testing, because there are all these tests for weak instruments, the Klein-Berger-Papp test and the modification of the Anderson-Rubin statistics. How do you apply this test in this case? It's a very good question, and I think that is something that practitioner would love to know how to do, because I think it's actually a question that I get asked very often. Like in this case, I have to be happy using a likelihood ratio test, which doesn't really account for the nature of the model, because I'm just taking the assignment equation and seeing if in that equation there is enough grip. But I guess that one will have to think about more general class of tests which actually account for the nature of this particular model, and that I think is very challenging. And I guess you have also thought about it, and it's not particularly easy to do that. But yeah, these are very good points. Thank you.
Thanks, Samuele. Any other questions? No. Well, it's 10 after 10 p.m. for me, so I would like to thank everybody for being here. I would like to thank Samuele for a very nice talk.
Thank you very much for having me.
I think I heard some child voice in somebody's background, and I wonder if this is yours somewhere.
Yes, mine. Yes.
Yeah. Do you have
It's
a
mine, but I have a
how
small
old is
baby.
your
He's
baby?
He's 16 months. Yeah, 16 months. So he's
Oh
pretty
wow,
young.
great! Yeah, that's excellent. We had a participant right here. Must be enjoying what you were saying to us.
Well, I don't know, but
All right. Well,
thank you.
congratulations, and yeah, let me
Thanks.
wish everybody a safe Easter,
Thank
a safe
you.
Catholic Easter, and a good weekend. Thanks again, Samuele. Very good to see you.
Thank you.
Very good
Thanks
to see
everybody
everybody.
for the invitation.
And if there are no questions, I'm gonna just, I guess, Alexander or I would stop the recording, right, Alex? Do I stop the recording? Let me just, I guess I'll go ahead. Yeah.
Okay.
Yeah. All right. And thanks again.
Thanks for the
Yeah.
invitation.
Let's hope that the restrictions will slowly subside and we'll be able to travel and perhaps we'll see each other. There's, by the way, the WIPA. Are you at the WIPA conference by any chance?
No, so Chris is gonna be there. He's gonna present a joint paper, but I'm not gonna be able to make it this year, unfortunately. I have with the baby, traveling has become a little bit of difficult.
Yeah.
So I think unfortunately I'm gonna have to skip it this year, but hopefully there are gonna be occasions in the future to see each other.
Yeah, definitely.
Thank you very much again for the invitation. And
no, thank you.
Well, I hope you enjoy the talk. Thanks.
Yes. Good stuff. All right. Take care, guys.
Have a good one.
Stay
Bye.
safe.
Take care.
Bye.
Bye.